They like blanks, like someone walking in heels.
Anybody know how to draw the pinky emoji?
Do like the eyebrow.
No, isn't there like a little finger thing that happens like?
Oh, wait, yeah. Like,
Ooh, draw this for me. Who wants to be an artist? Go.
wait, I'll try. I just
Come up
need to
here.
have the reference.
These are weird. Class
This one is
participation.
the one.
Yeah, that one. Thinking emoji. Are you awake? You don't look like you're awake.
I'm very tired. Can I put this up here again? Is that up to your standards?
Looks great.
Okay. I can't draw for crap, so.
Did you say?
I read the question a lot. I think you born as one.
How are the dinosaurs, bro? That had to be
Alright.
so cool.
Were you alive enough to or like when you're
Yeah, my thing.
Oh gosh, it's bad. Look at all of them. Look at all of them. They're so bad. It's so mean. Wait, this one's a bad one. Sorry, I'm just really kidding myself now. You just stand there with all these tennis balls. For a second, I thought we had studied wrong today, and I got really sad.
Thanks.
No, I like that class just goes too late and it's Friday.
Keep the class, I think it's hard to teach to the group, and as large as it is, and the diverse as it is.
Wait, it was because we got ice from Atherton.
Oh, I definitely just sit.
Yeah.
That was horrible.
Yeah.
And it breaks so much.
But it literally. Visual visualization. Okay, okay.
Visual repolarization.
We got like 40 minutes and you're like,
I think I want to play, but she put a concept on there that she told us, well, that wasn't on the list, she told us we needed to know. So that was fun. But it's fine. Now I can focus on studying for this class, like this whole weekend, because I've been like behind. Because of that class.
and like, you know, they're so long, and I like this, they have a specific name.
I played intramural game yesterday. Yeah. But I didn't really play much, obviously. But it's Caleb's team. Yeah.
At one point, I
Oh my gosh, yeah, Mike was telling me.
Really?
Yeah, like, he said that like you guys can play Lambda guys. What's a Lambda guy?
Yeah.
Yeah, I was looking at them before you.
Yeah, like originally they used girls soccer team, I guess, but none of them could play. So
Well,
they just
yeah.
decided all these Lambda guys.
I know there was a guy that was like huge, bro. He was expanding them.
Oh yeah, he's talking about like a six guy.
Yeah, I was like, this guy's got to be 6'7". And let's see. I don't know, but we lost.
Yeah, you're like,
Well,
It was fun though.
Mike
It
was
was
telling
fun.
me you guys were like 2 seed or something.
Yeah. Said they were supposed to win. I was like, okay, I'll just go just in case you need me. Yeah. They got really quick.
yeah.
I looked it up. Starlight was founded in 1971.
I'm pretty sure that's what
Yeah.
it was for.
Really? Wait. Okay, that math would be 29 plus 26, 40, whoa.
Whoa.
Whoa, 50.
But like,
Jesus. Yeah, he has a daughter our age.
245.
Yeah, 1973.
Wait, how do you Loki know
Looked up his
that?
LinkedIn the other day.
Oh, dang. He went and flipped it. Oh my gosh, this is like an absolute mess.
I mean, yeah. 2 years.
So 95 minus 22. 95 minus 22. He graduated undergraduate at 19.
You should start doing question of the days. That made it like fun.
Yeah.
Which dinosaur do you miss the most?
I made that same joke
I
earlier.
think it's probably the pterodactyl. I used to hitch rides on by grabbing on their feet.
I think you yourself were a dinosaur. A Stegosaurus.
We get the money to create a museum.
Just go to his office.
Bro. That was awesome. Oh my gosh.
We don't have to be here. I can just give you the exams and. Actually, just give you the exams. Go. Good plan.
Let's do it.
You said you don't have to worry about people anywhere else.
I like that.
I mean, it doesn't really change much.
Oh my god.
Right. Yeah, I try.
You do. Front back.
Wait, I'm so kind of confused.
Wait.
When the OH, the O with the plus charge, and it leaves, why is there, it's still, oh wait, never mind. Sorry, I just confused myself.
I have to be specific species, especially with the
Oh my god.
All right, good morning, everyone. Happy Friday. Question of the day. What do you think? Who's older, Starbucks or Estep? Who votes Starbucks? Raise your hand. Who votes Estep? Starbucks wins. Starbucks 1971, Estep 1973. That was my morning revelation as my Starbucks cup said established 1971. I'm like, damn, Starbucks is older than I am. So there you go. Something like that. Okay, so we've been talking about using the cyclic acetal, which really is no different than the acetal. But the cyclic acetal makes it a little harder to break. So like at this step here, which I'll go through this whole thing, when you make this carbocation, this group is still hanging around in the vicinity. And so the likelihood of it reattaching goes up. So you have a more robust protecting group on with the cyclic system than you do with the acyclic system. Okay? The mechanism for the cyclic acetal formation is exactly the same as the acetal formation mechanism we learned before. It's just now both of your alcohols that you're going to use to add in are attached to one another. Okay? So if we go through the mechanism, first step is still the protonation of the carbonyl, the aldehyde or ketone, to make the resonance stabilized intermediate. Okay? That's just a heteroatom with a hydrogen and a plus charge, so we either pull the hydrogen off or kick the electrons, which gets this structure, which means the only thing we do is go back and forth from here. So this is our reactive species. We've played with carbocations lots of times. So carbocation substitute, eliminate, rearrange. Not rearranging the resonance stabilized. So we're looking at a substitution versus elimination competition. The elimination makes an enol, which we know isn't a stable form, and so we're looking at coordinating. So what's available to coordinate? Alcohol in the form of the diol comes in, adds to your carbocation, makes your intermediate here where there's a plus charge now on that oxygen. So that's just the heteroatom with the hydrogen and a plus charge. So we either kick it out as a leaving group, go back to where we came from, or we pull the hydrogen off to get to our system. Okay. This is actually our hemiacetal state right here, because we have both the OH and the OR group at that position. Okay, so we haven't done anything different than what we did before. Like I said, the only difference is that that OH is pendant, hanging around, but it doesn't actually participate in the reaction until we start doing things with the second addition. Okay, so remember, to facilitate the second addition, we need to protonate the alcohol to kick this out as a leaving group. So this is the stage that everyone gets stuck because it's neutral and there's no charge to drive your attention. When that happens, you go back to the conditions of your reaction. Make sense to everyone so far? Okay, so our conditions are acidic. I chose just to put HB+. This is a simple thing to do with these acidic and particularly the acidic mechanisms with these ketones, because there are so many different species that can potentially act as the base in your mixture, right? Anywhere we have an oxygen essentially could be that proton acceptor. All right, so instead of trying to keep track of which one's most likely, you just do a generic B. Okay, and under acidic conditions, it's always going to be a B neutral or an HB+. When we start doing the basic mechanisms with B, it's a B-, okay, or an HB neutral. All right, so we'll see a lot of these as we do lots of mechanisms in this chapter. Okay, so HB+, protonates either here, which goes back to where we came from, protonates here, which not going to kick that off to make a primary carbocation. So even if that does protonate, it doesn't do anything. Okay? So the only thing that's going to get us somewhere is propane here. So we get to this species, heteroatom with the hydrogen and a plus charge. So we lose the hydrogen, go back to where we came from, or we kick it out as a leaving group, which generates the resonance stabilized intermediate. With me so far? All right, and then this is where the second equivalent of your alcohol comes in, and that second equivalent is right hanging out there. So it comes in and attacks, makes the protonated version of your cyclic acetal, which is just a heteroatom with the hydrogen and a plus charge. So we pull the hydrogen off, go to our product, or we kick it out as a leaving, going back to where we came from. So all of this is an equilibrium, like I said. So we have the ability to go back and forth. All right. So with the back and forth thing that we have, this is where the hydrolysis comes in. So this is going to be how we go back from the acetal to the ketone or aldehyde. Or specifically, when we're dealing with our cyclic acetals, it's going to be how we remove our protectant. All we do is throw in lots of water under acidic conditions, and it's going to push this equilibrium back in this direction, because what we'll have is lots and lots of the water nucleophile that's going to want to react, and it starts outcompeting the oxygens that are part of the acetal. Okay? So we're going to see when we do the hydrolysis mechanism, we're essentially going to walk backwards from where we are here. Okay? So we start with the acetal. This time, instead of having lots of alcohol around, we have lots of acidic water. Okay, so we protonate this to make it a good leaving group. That goes away, and now the nucleophile that's floating around in a great abundance is our water. We go ahead and attack there. You can attack there. You go here and get that up. It's the same thing. Right. Abundance of water to come in and attack our carbocation and make our protonated hemiacetal species. Okay, so going backwards from this, if we have lots of water, this can go get protonated again. Okay, and now we kick this off as a leaving group to go here, and then water comes in to get to this species. Okay, it's just walking the pathway the opposite direction. And we're just using Le Chatelier's principle to go backwards and forwards. Everyone with me so far? Add in, get here, head around with the hydrogen plus charge, pull that off, get to our neutral species, get stuck. Okay. Lots of alcohol, go back this direction, lots of water, we're going to continue in this direction. So, one conditions of a reaction, which is the acid, so we're going to protonate. We need a protonate here, which goes to this one, or protonate here, which gets us to a new species, if we go in this direction. So we got the protonated heteroatom with a hydrogen and a plus charge, so we kick that off as a leaving group to go to our resonance stabilized intermediate. Okay. And then heteroatom with a hydrogen and a plus charge, simply pull that off to get back to our ketone. Make sense to everyone? Okay. Any questions? So the mechanisms are a lot longer under acidic conditions, but they're easier to follow because if you just kind of keep the heteroatom with a hydrogen and a plus charge in your mind as to how you do things, or carbocation behavior, it will drive you to understand where you're trying to go. The biggest mistake that I see people do is they get confused a little bit in this equilibrium and they'll forget which is driving the reaction. So they'll go through and get to the hemiacetal, and they're supposed to be continuing in this process, and they'll end up going back in the other direction as they get confused about what they're doing, and they end up back where they started, which is fine. This is not what they're doing. Trying to show the mechanism for the product. So just pay attention to where you're trying to go and make sure the product that you're trying to get to is what you're actually for. Okay, make sense? Any questions on that? Okay, so that's acetal formation and hydrolysis. All right, next thing. It's dithiene formation. And I'll tell you why we want to form dithiene after I show you how to form that. All right, so what dithiene is, and we talked about this first semester, and this is dithiene. So remember we talked about our cyclic ether, you probably don't remember this, but we talked about cyclic ether nomenclature, and we had our ethers that we started with, which is our cyclic ethers of 3, 4, 5, and 6 atoms in the ring. And we said the way we name these is by using suffixes. So the 3-membered ring was an irane, the 4-membered ring was an ethane, the 5-membered ring was an olane, 6-membered ring was an ane, and then we used ox as the prefix to indicate that the oxygen was in the ring. Okay, with me? Okay. Then oxygen and sulfur are right above and below each other in the periodic table, so we can use, instead of ox as our prefix, we can use thi when we're dealing with the cyclic thioethers. Okay? So we have this, this, and this. That's our analogs here. So this would be an oxane, because ane is a suffix. This is a thiene, right? Make sense? Okay. If we look at our structure here, it's still a cyclic, 2 carbons on either side, but we have what? We have 2 sulfur groups. So what do we do when we have 2 of something in a name? Di. Okay, so this is a dithiene, and more specifically, it's a 1,3 dithiene. Right? You're actually going to be able to start with this as a starting material in synthesis for this chapter, because we're going to see why we care about this and how we can use it synthetically to make pieces pretty easily. Okay? But that's, when I say 1,3-dithione is a legal starting material, it's this compound. Okay. Everyone with me so far? All right. The way we make this is going to be essentially analogous, and I wish I would have kept the cyclic acetal. Just write that here again. So remember, our cyclic acetal looks like this. So this would be a dioxolane for the 5-member grain, dioxolane. All right. But the way we make this is going to be analogous to the way we make this because sulfur and oxygen have similar activities. Okay, so the method that we use for the cyclic acetal formation is going to be identical to the mechanism that we use to make these dithiones. All right, you with me? Okay. So let's do an example and mechanism. So we'll do the unsubstituted one first. So we want to make this. It's going to be a 1-carbon carbonyl with 2 hydrogens on it. So this is formaldehyde that we want to start with here. And then the piece that we want to add in is right here where these are going to be SHs. Okay, so this is propane, 1,3-propane dithiol. Like that we're going to use to get to that structure. Okay, and what kind of conditions do we want to do this under? Acidic. Okay, so we'll throw in some catalytic non-nucleophilic acid. So, and that then will get us wherever we had our C double bond O became a C to individual bonds to 2 oxygens, right, with the acetal formation, and then whatever R groups we had. Here, it's going to be the C with single bonds to the 2 sulfurs with whatever they're attached to. Okay, so that's our C double bond O. There's our 2 bonds to our sulfur, and then these sulfurs are attached via the 3 carbons, 3 CH pieces to make the 6-member. Okay, with me? All right. So mechanism is exactly what we just wrote for the cyclic acetal formation. It's just now the sulfurs are there in place of the oxygen. All right, so let's do this. The risks are going to be sore after they were writing all these mechanisms. Okay, so our acid is going to drive our reaction. We have the carbonyl that wants to be protonated because it makes the resonance stabilized system, which makes it the most basic site in the reaction mixture. So with this, protonated form, which has resonance structures. Like so, plus OTS minus. We don't tend to draw the counter ions on these because we have enough things we're already drawing. So if it doesn't really participate, we don't worry too much about it. All right, so now head around with the hydrogen and plus charge, lose the hydrogen, go back to where we came from, or kick the electrons, get you to here. Okay, so we're going to react here. Now our nucleophile is your thiol species. Comes in, attacks your carbocation. And gets us here, and that sulfur started out neutral, gave up electron density, so it becomes positive, and the carbon was positive, gained electron density, so it becomes neutral. Okay, how do we add them with a hydrogen and a plus charge? We don't care if this is a sulfur, nitrogen, oxygen, it's still the same rules. It either kicks off as a leaving group, which goes back to where it came from, or pull the hydrogen off, electron density onto the atom. And what are we going to use to do that? Well, once again, it's going to be anything that has nucleophilic character. So this is where the B with the lone pair is kind of the best bet. It could be one of these. It could be the water that you that gets kicked off as part of this mechanism. It could be another equivalent of this. It could be another carbonyl. Okay, so you have lots of options there. Easiest thing is just draw the B with the lone pair and keep your life less difficult than it is already. Okay, so we're going to use this. Pull the hydrogen off, electron density onto the sulfur, and we get to our hemi species, which is neutral. Okay, the hemi, not acetal, because this isn't a sulfur, but it's the hemi sulfur version of the acetal, the OH and the SR in the species. This is where we get stuck because there's no charge there to direct us. So what do? conditions of the reaction, which are our acid. We got our Hb plus, which we just formed here, right? So it can reprotonate your sulfur, going back to where we just came from. It can protonate this sulfur, but if we try to kick that out of this lead group, that's a primary carbocation, not going to go anywhere. So that just goes on, falls off, right? Goes on, falls off, back and forth here. You do the alcohol, and this gets you somewhere new. Okay, so go ahead and protonate our alcohol using the lone pairs on the oxygen, kicking the electrons out of the base. Okay, and where it gets a little screwy is where the bond angles start looking weird when you do this. So you really should change them as you go forward. So we got the trigonal planar sp2 hybridized carbon there. All right, so we get there. The resonance structure. Draw. Okay, so it's the exact same mechanism we were doing with our cyclic acetal. Nothing has changed apart from the fact that these are now sulfurs instead of oxygen. It's the same exact mechanism we just drew. Okay. Questions so far? For whatever reason, students struggle more with this mechanism than they do with the acetal mechanism, but they are literally identical. Okay, so just keep trying to reinforce that to your into your mind. Okay. This thing's not going to get us anywhere because it's a heteroatom with no hydrogen, so the only thing we can do is kick the electrons back to this structure. So it's the carbocation that's now going to react. And this is where we have to think about where we want to go, because there is lots of stuff floating around in the mixture. What are we trying to make? We're trying to make the bond to the extra sulfur, right? So this is where then the electron pair on the sulfur comes in, attacks that carbocation to give us our cyclic form. So now we're to H plus, like so. Okay, heteroatom with the hydrogen and a plus charge. So we either kick it out as a leaving group going back to where we came from, or we pull the hydrogen off. So, and make our cyclic acetal, but with sulfur in place of the acetal. It's the dithione that we made as our product, plus Hb plus. So all of these steps that we drew are all equilibrium steps. Okay. The difference that we have here is you cannot go back from the dithione to the aldehyde or ketone with acidic water. Okay. The sulfur carbon bonds are stronger, and you can't break them just with them. You have to do a completely different process to break this dithione. This is one of the reasons why we're going to use it to do what we're doing instead of acetal. Is number one, the acidity of these hydrogens is increased relative to your acetal, which becomes important. And then number two, this is a much more stable framework, and so it can endure the conditions of the reaction you're trying to do without falling apart. Okay. Does that make sense to them? Okay. But other than that, the actual formation process is the same, just our equilibrium, even though it's an equilibrium possibility, does not favor going back the other direction. So we put these in, it's going to want to stay over here once you make it. Okay, go ahead.
When you protonated the alcohol on the bottom half,
Yep.
right, did you just like skip something that kicks off?
Probably. Where did I go? Yeah, I did. I'm sorry. Yeah, so this step, you get the OH, and then you kick that off. Okay, thank you. Let me write this in. All right, so this, to get to here, you have to actually make this. You guys are supposed to catch me when it happens. All right, so this step right here, plus this, gets you that around with the hydrogen and a plus charge. So we kick that off, which now gets us to here. Okay. I apologize. Lots of stuff to write, lots of stuff to explain. With me? Everyone good? Okay, so insert, going from here, Hb plus goes to here, and then there it just kicks off the leaving group to get you here to continue the process. All right, we all good so far? All right, now that we know how to make these diethylamines, let's look at what we can do with them. This is the alkylation of diethylamines. Couple notes. This does not work with cyclic acetals. Cannot do the same reaction with acetals, only with diethylamine. The reaction goes as follows. We can take a strong base and actually deprotonate the hydrogen. This does not work with acetals. They are not specific enough with acetals. Sulfur stabilizes the negative charge here better than the oxygen does, and therefore the acidity of this goes up. And it's that whole thing when we talked about acidity and basicity with periodic trends. Remember, we talked about the fact that as you go, electronegativity goes across the periodic table from left to right and from bottom to top, but the ability to stabilize that negative charge goes across the periodic table from left to right and then from top to bottom. Okay, so that sulfur can stabilize the negative charge better, which means that when you're putting negative charge over here, it's going to be able to take more of that electron density than oxygen, okay, which increases the acidity of this. That all make sense to everyone? Okay, so the base we're going to want to use here is N-butyllithium, which is just an RLI that we already learned how to make with organometallic reagents. So it's the 4-carbon thing is an N-butyl group, normal butyl. Get your minus charge here and your plus charge on your lithium. And so this is a very strong base because that negative charge is on sp3 hybridized carbon. Carbon does not want the negative charge. And remember, sp stabilizes the charge better than sp2, which stabilizes better than sp3. So this is really not happening. Okay, so this has really increased basicity, which allows us to pull this hydrogen. Okay, so this is just proton transfer reaction that's going to happen. All right, so we're going to go ahead and pull off one of the hydrogens, keep the electron density onto that carbon. Which makes the anion. Lithium is a spectator ion on there. You can draw it if you want, but you don't have to. Okay. So we can get to this point. The solvent in here is usually either THF or ether. It has to be one of your polar aprotic solvents. So acetonitrile does work. Acetone will react with N-butyllithium, so you don't want to use that one. EMF can kind of react with that one, which is why we stick to THF or ether. Okay. So we get here. And then what we do is in a second step, we want to alkylate this. And this is going to be an SN2 reaction. And this then is just our Nu minus. Okay, so we just have to throw some alkyl halide or alkyl tosylate in that can react. This is our Nu minus that's going to attack and kick out. Since this is an SN2 reaction, what are our limitations?
No tertiary.
No tertiary carbons, no sp2 alkyl halide. Still following those same rules as before. Okay, so we have our X, THF or ether again, because we want to do an SN2 reaction. And then all that happens, that comes in, this is backside attack, takes that out. And allows us to attach an R group to that position of the dithion. Okay. If we want to do it again, we can do it again. Repeat the process. Step 1, N-butyllithium, THF. Step 2, alkyl halide, THF. That would deprotonate here, make the negative charge, comes in, does the SN2 on that carbon. And allows us to put whatever alkyl groups we want, as long as they follow the SN2 rules, on either side of that carbon. Okay. So So fairly simple way of doing it, okay? Making carbon-carbon bonds without too much trouble. All right, and then what's nice about this is like our cyclic acetals that we have, where we can go back to the aldehyde or ketone that we started with, or in this case, since we changed what we started with by making 2 carbon groups, we're going to get to a new carbonyl compound through this process. You cannot use H3O plus. Okay? H3O plus does not work, so not H3O plus on the diethyne. And instead, what we have to do is use mercury. Use mercury chloride in water. And the reason this works is that mercury and sulfur absolutely love each other and love forming bonds with one another. So if you actually have a mercury spill, you know how you treat it? Sulfur. You sprinkle sulfur on, it coordinates, and then you can sweep up the that new coordinated complex and remove it. Otherwise, you're trying to chase little balls of mercury all over the place. I had to do this in grad school, but we use a lot of mercury. Probably explains why I'm doing that. But yeah. So anyways, loves of mercury. So this is the way we're going to cleave this. You do not have a mechanism for this. It's inorganic chemistry between the mercury and the sulfur with electron transfer processes. Not something we can easily draw with arrows. So you just need to know that this is going to do what we want, which is to turn this back into the C double bond O that we used to make this diethyne in the first place. So now, though, we have the new R groups here, and then this carbon goes back to the C double bond. So this is a way of really, we can start with an unsubstituted aldehyde if we wanted to, formaldehyde, and put 1 or 2 different R groups on there to make a new ketone or aldehyde. Okay. Or we can start with this diethyne itself and put whatever groups we want on here and then unmask it to get to the carbonate. Okay, you with me? Yeah, Miriam.
Use this instead of the ochem.
Yeah, so students will love this reaction. And there's no, how do I put this? Grignards work really, really well, and we've already learned how to do that. The nice thing about this is commercially available, and you're doing SN2 reactions. You're not dealing with Grignards are a little sensitive, and we're going to do Grignard reactions in the lab, but we used to have you make one, and you got to see how you're like initiating to make the Grignard was a little tricky, and you had to kind of play some games to get it going. You throw some iodine in there. So making Grignards isn't always the easiest thing to do, where deprotonating this is really easy. It literally is just taking this compound off the shelf, put it in dissolve in THF or ether, and then dropping in some NB-lithium. It deprotonates, and then the SN2, which we know is a really easy reaction, because that's what we learned in this very first reaction we left right for proton transfer. So that's the advantage, but they both go hand in hand. So it's 2 different pathways, but students find this easy because they see the diethyne and they're like, oh, I want this side to have look like this, and I want this side to look like this, so I can just use my diethyne, put it in, and then throw in my mercury. So it's a little less thought-provoking, I guess. But
When you make the diethyne, is it always going to be in the 1,3 position?
yes,
Okay.
for the diethyne. So the reaction still works with the 2, but then it doesn't quite stabilize as well when you're doing this reaction. So you want to do the 1,3 diethyne for the alkylation, but any diethyne can be made with any ring size here, just like you can with any cyclic acetal.
Okay.
Okay. Make sense? Remember how I told you we were writing like full board mechanisms all the time and learn 6-7 reactions a day? This is what happens. This is where we are now. Okay, so not too bad. We understand how they all work, but this is how it works. Okay, so let's try to do an example of using this synthetically. 2 examples. And then we can start getting to nitrogen as nucleophiles with the carbonyls.
Wow.
Okay, legal star materials. 1,3-dithiene, alkyl halides of 6 carbons or less. Reagents, or not reagents, inorganic reagents, and solvents. Okay, no acetylene in here, so you can make acetylene if you really want to, but it's a lot of extra steps. So trying to keep you focused on certain techniques as we go forward. And the easier one first. This one. And then the harder one. So looking at this, what I see is we get the carbonyl here in the middle. I got a 1, 2, 3, 4 carbon piece on this side with primary carbon here, right? So SN2 worked really well. I have a 3 carbon piece here with the primary carbon over here. This looks like a perfect candidate for that dithiene reaction we just learned, where I have, okay, this is going to come from my dithiene. I simply have to add these 2 pieces on and then unmask. And so you can do this with your Grignard. We could have that be, start with the alkyl halide, convert it to the alcohol, oxidize the alcohol to the aldehyde, start with the alkyl halide, make your Grignard, add it in, get the alcohol, oxidize it back up, and get your product. Right? That's what we just did for synthesis on Monday/Wednesday. Right? Nothing wrong with that. But this, that sounds a lot easier, right? Dithiene, deprotonate, add this alkyl halide, deprotonate, add this alkyl halide, and you're done. Okay, so let's write it in the forward direction. Since I thought it out. All right, so I want that to be my legal starting material. First step, N-butyllithium, UHF. Second step, let's just add the propyl bromide. And alkyl halide is a legal starting material, so that's all right. Good SN2 solvent. So that will get me to there. And then I just repeat the process. First step, N-butyllithium, UHF. Second step, this time I want the isobutyl bromide. Let's keep it in the same direction, I guess. This is there. Okay, and then mercury chloride, H2O. Unmasks that to make my product. All right, what's the thing that students want to do that's actually wrong, but they always want to cheat and try to do it? Figure it out. Yeah. 2 equivalents. I knew you would know that. What's the shortcut I can do that's wrong? That's Michael. Okay. You can't do 2 equivalents of N-butyllithium. You're not making a dianion. That's not a thing. You can't put 2 negative charges on that carbon at the same time. Makes sense? So you have to do it one at a time. All right. Questions? Okay. So here, same idea, right? Let's have our 2 carbon pieces, 1, 2, 3, 4, 5. And let's start with bromobenzene. Put that in there. That's legal starting material. Okay. Good? What?
Tertiary.
You can't do SN2 on an sp2 carbon, right? How many times do you think I have to write this on these types of syntheses where the students get into dithiene land and try to do it on this? Too many, yeah. Don't do that. So this side I can put on there, but this side I'm going to have to use, going back to Miriam's question, more the traditional Grignard pathway to put this side. Okay, make sense to everyone? Yeah. Okay. It's right in the forward direction somewhere. Okay, so we'll go ahead and start with our dithiene. First step, N-butyllithium. Second step is this 1, 2, 3, 4, 5 carbon piece with the alkyl halide at the second carbon. And gets me to there. Okay. Now what I have to do is I have to unmask this because I can't be protonated and added as a nucleophile. So I now have to use this as my electrophile and add my carbon piece in through my other carbon forming reactions. So we have our mercury chloride, H2O, and that now gets us to here. So, and then we want to add in phenyl, magnesium bromide, ether, followed by H3O plus, and which would get me to here. All right, I did addition, so this comes in, connects my carbonyl, picks it up to the O minus, and the O minus is protonated with H3O plus, and then how do I get to my carbonyl that I want? PCC or Jones, right? Here, so PCC, and some HCl2. Makes that work. What am I missing? So make Gringer. Okay, so bromobenzene is a legal starting material here. That, how do I make the phenyl magnesium bromide? How do I make that Gringer?
Bromobenzene with
Magnesium and
THF.
THF or ether. Ether would be the more common one, but both work. And that inserts the magnesium between our carbon bromine bond. Makes sense. So that would be our synthetic pathway here. Could you do it 100% through Grignard? Yeah. You can do 5 carbons, so you still have to add this in. So you have to start with something like formaldehyde, make this Grignard, add it in to get the 6 carbon, right? No, I said 6 carbon, so 6 carbon, you have to start with the aldehyde and then the other one. If it was 5 carbon, you would have to add. Right? So once again, always read your legal starting materials and kind of plan out the pathway that's going to work best. The main point of this is to show that you can add that phenyl group directly via the SN2 through the dithion chemistry, even though you're really going to want to, because you get it in dithion land and get happy about it and start doing that all the time. Okay. Questions? Okay. Next topic. The good news for all of you is that I learned a long time ago that traditionally the way a lot of books present these things is they go through and they do the aromatic chemistry. So you find what aromaticity means. I know at least one section of doing this. You find benzenes, like what makes benzene special. You do benzene chemistry, which is really basic. And just pull hydrogen off, add a new group in, and you have these reactions that you memorize. Students don't have any problem with that. They go to Diels-Alder, really simple, making 6-membered rings. And then end of the semester comes, we hit all of this. And then the acid derivatives, which ramp up even more because there's 35 reactions that we're going to learn. They're all the same, but there's a bunch of them, right? And that's what you're doing at the end of the semester when everyone's frazzled. Okay? Complete disaster. It's not good mentally for any of the students. So what I learned a long time ago is it's much better to go through this stuff, which feels like a little bit of a ramp up from where we've been, right? With the mechanism being longer. Get through it, endure it, and then, so it's this right now, and then it's this going into the end. Does that sound better than this?
Yeah.
Yeah, it is, just trust me. I've done it both ways and it's not good. So good news is just tough it out through lots and lots of mechanisms that we're doing, and then things get easier at the end. It doesn't mean you can stop working, but it's not quite as involved, not long, not as many reactions, etc. Good? All right. That's neither here nor there. Okay, next thing is our nitrogen nucleophiles, which we won't get through all of them, but I can introduce them at least as a framework to start from for Monday. All right, so addition nitrogen nucleophiles to aldehydes and ketones. All right, so what we're saying here is that we're going to start with, and I'm going to write this a little bit weird for a reason. All right, this is still aldehyde or ketone, which means R prime is either a carbon group or a hydrogen. R group can be a hydrogen or carbon. Right? We have our framework here. The idea is that it doesn't matter if it's an aldehyde or ketone. Can't be an ester, amide, acid halide, any of that stuff, just like all the rest of these reactions we've learned so far. That's carboxylic acid derivatives, they come later. This is all just aldehyde and ketone. Okay. Where things get screwy is depending on the character of the amine that you're trying to react with, you will get different products. The mechanisms are essentially the same, but the products are different. Okay. If we react with a primary amine, okay, so this is something like this, R double prime NH2. So the nitrogen is attached to one carbon group and two hydrogens. That's a primary amine. Versus a secondary amine. Okay, which would be R double prime N, R triple prime N, H, right? Two carbon groups and a hydrogen. We do this with catalytic acid in both cases. Okay, and it turns out here that you got to be real careful with both of these. You must control your pH curve. Okay, if you get too acidic, you start protonating all of your amine and you shut down the nucleophilicity, so it can't add as a nucleophile. Okay, does that make sense to y'all? We're not going to worry too much about it, but if you're actually doing this in lab, you have to be very careful. And sometimes HOX isn't the best acid. You can use like mild acetic acid, dilute acetic acid to do it to keep the pH right. But the point of this is that the primary amine is going to react differently than the secondary amine, and the tertiary amine does not react. And we'll see this as we go through the mechanisms as to why. All right, so this is where there's no hydrogen. Our nitrogen is the tertiary amine. Will not react. Okay, with me? All right. The reaction product that we get out in both cases, no, not this. The reaction product we get out for the primary amine, let's start there, is going to be that we replace our C double bond O. So we're going to replace the oxygen to a bond to nitrogen. So it's going to go from being a C double bond O to a C double bond N. And then whatever carbon group we have on there still is attached to that nitrogen. Okay. So we still have our R group on that nitrogen. The hydrogens are going to go away. And this compound in organic land is called amines. And I think in biochem, I know like probably things shift bases. Why? I don't know. Okay. Amine for organic land. All right, when we do this with the secondary amine, we still are going to replace our bond to the oxygen with a bond to the nitrogen, but because of the fact that we only have one hydrogen to remove, the character of that bond is going to be different. Okay, so we're not going to do a double bond to the nitrogen like we do up here. We're actually going to have a single bond to that nitrogen. Okay? And the double bond is going to be localized elsewhere. So where it goes is it's still going to be attached to this carbon, but it's going to go to the carbon, which we call the alpha carbon, the carbon next door to the carbonate. Okay? And if you have it on both sides, you can get a mix of products. With me so far? And this mechanism will help make all of this make a lot more sense as to why these things happen. But this is what we get. We get what's called an ene for the double bond, and then for the nitrogen, amine. Okay? So enamine, and the two carbon groups that are attached to that nitrogen stay attached to that nitrogen. Can't remove this. Right, so we get our R double prime. Okay, so secondary amine with an aldehyde or ketone will make what's called enamine. Ene, amine, double bond, and nitrogen. Primary amine with aldehyde or ketone make what we call an imine, IME, which is the C double bond to nitrogen. In both cases, the carbon groups stay attached to the nitrogen. Okay. just the hydrogen you're removing. Good.
Is there any selectivity with the double bond, like?
No, if you have hydrogen on both sides, so if this was that, you're gonna get double bond here and double bond here,
Okay.
okay? And you have to draw both across that when you go on. But we'll see this mechanism stuff. Yes, we're not gonna have time to go through the mechanisms today, but I wanted to at least get us primed for what we're gonna look at. And like I said, the mechanisms start essentially identical. The only thing that really changes is get to the point on this one where you have an additional hydrogen you can remove, so you do. And on this one, you don't have an additional hydrogen you can remove, so you have to divert your path a little bit, which gets you here. Okay? And when you have a tertiary amine, you don't even have the first hydrogen to remove, so when it comes on, the only thing you can really do is fall off, and you can't progress through the mechanism. Okay? So we should see this, if I present it right, mechanistically, that we're doing the same process for all three. It's just this one gets stuck here, so we stop, right? Can't do the reaction any further, no reaction. Primary amine allows us to go and remove both hydrogens all the way to what is kind of the sensible product, the C double bond N, and then we try to do it with secondary amine. And we got the one hydrogen, so we get to one place, we get stuck at this intermediate, and then we have to open up the other possibilities we have at that site other than pulling hydrogen with the nitrogen, which isn't there. Okay. With me? Oh man, I'm almost as old as Starbucks. This is hard work. All right, you guys have a great weekend. No homework or anything. Don't start the problem set still. We got a little bit more, and then you can start the problem set for the aldehyde ketone. Do review the synthesis stuff though. Let's make sure you feel really good about that homework assignment that I gave you. So making the Grignard stuff. Think about the diethyene, using that in synthesis a little bit. Make sure you feel good about that, and then you'll be able to start the problem set soon enough.
Yeah, bro, I looked at the comments yesterday, didn't want to do it. And I was like, what's going on? The first problem I